And we're back at it, folks. Today we're on to Unit 211. We're not going to finish 2.11 today. We'll finish it tomorrow. We won't have a whole lot to finish tomorrow, so you'll have a good opportunity to tackle the homework tomorrow, which is good because the homework assignment is a little bit larger than normal. You'll see when you go on to Schoology. Anyways, what is Unit 2.11? Well, it's just called Logarithmic Functions. Very vague title. But it's really just about the properties of logarithms and their graphs before we move on to solving logarithmic equations and their applications like semi-log plots and things like that. Also, we still haven't actually reviewed the properties of logarithms like expanding, condensing, and things like that. And you need to learn those before you can solve anyway. So today we're just going to really cement the idea of the logarithmic graph, how transformations affect it, and things like that. Okay, we've already discussed the domain of a logarithm, but let's talk about it again. Logarithms are the inverse of exponential functions. That means x's and y's have switched, which means domain and range have switched. So the domain of the logarithm is the range of the exponential. And since the parent exponential graph has a range from 0 to infinity, non-inclusive because it has a horizontal asymptote at y equals 0, the logarithm has a domain of 0 to infinity. Ladies, hey. The logarithm has a domain of 0 to infinity, and it has a vertical asymptote at x equals 0. Because all the x's and y's switch places, things like that. What that means is the argument of the logarithm, which here is just x, but whatever we're taking the log of, the argument of the logarithm must be positive. Always. So just some properties of the graph. The x-intercept is 1, 0. Why? Because it's the inverse of the parent exponential, whose y-intercept is 0, 1. Since the parent exponential has no x-intercept, the parent logarithm has no y-intercept. The y-axis, which is x equals 0, is the vertical asymptote of the graph of the parent logarithm. Why? Because the x-axis, y equals 0, is the horizontal asymptote of the exponential. See, everything's just switching. X's and y's are just switching. For exponentials, if the base is greater than 1, you had an up and to the right graph, an increasing function. Well, that's going to be exactly the same for the logarithm. Up and to the right, increasing function. For the parent exponential, if the base was from 0 to 1, you had a decay graph, which was decreasing, which is the same for logarithm. If the logarithmic base is between 0 and 1, then you have a graph that is down and to the right as well. These are all the same 3 points that the parent exponential has, just x and y have been switched. And just like the parent exponential curve, the logarithmic curve is smooth, continuous, no sharp corners or gaps. All that stuff we pretty much already know. We've already graphed logarithms. Remember, we talked about figuring out where the asymptote is, what makes the argument equal 1, what makes the argument equal 1, because then you'd have log base b of 1, which gets you one of your special logarithms, and then also what makes the argument equal base, because log base b of base is the other special logarithm, and from there you just connect your dots. We did all that, correct? Yes? Great. For these questions, we're going to be finding the domains of logarithms algebraically. The rule is that the argument must be positive. So you take the x plus 5 and you make sure it stays greater than 0. Very easy. Subtract 5 from both sides. And we get that a domain is x is greater than negative 5. I'm a big fan of interval notation though. There you have it. On the AP exam, because this is my first year as an AP instructor, I don't know if it's interchangeable on the AP exam. I don't know if they have one they require or prefer. I'll ask Miss Bluebaum. She's better than Google. She's been teaching AP forever. What do you think about that? Set the argument greater than 0, solve for x. Pretty easy? Yes? Yep. Pretty easy? Okay. This one is fun. I like this question because it's been a long time since we've done this. But we have done this. That was part of topic 1. Rational inequalities. The way that we tackle these is with sign diagrams. So we have to find our critical values, reminding you what critical values are when you're talking about rational functions. Critical values are places where it equals 0 and places where it's undefined. So how can we make this fraction, how can we make any fraction equal 0? Well, can you divide by 0? No, then that wouldn't make the fraction equal 0. What would make the fraction equal 0? Make the top equal 0. But you said make the bottom equal 0. Why can't you divide by 0? What happens when you try? Error. It's undefined. So that finds us the other critical value. There. If you add x to both sides, you'll see that we have a critical value at 1 equals x. So x equals 1. And if you subtract 1 from both sides, you'll see we have another critical value at x equals negative 1. This one is undefined at x equals negative 1. The only reason why I'm writing it like that is because on our sign diagrams, technically your discontinuities are supposed to have these little like asymptotic lines above it. That way you know that's literally a place where your graph doesn't exist. So let's be really clear here. X cannot be negative 1 because I can't divide by 0. X can't be positive 1 because it would make the argument equal 0, and we strictly need the argument to be greater than 0. So this is also a place where our graph is technically undefined, but I'm not going to put a little line right there because I'm actually trying to identify where this is positive and negative. Alrighty. The way that we use a sign diagram is we take a representative number from each of the 3 zones and we put it into the top and the bottom and we just look for the symbol. Now we don't care what the value is, we just care positive or negative. So let's take a number like negative 2 because that's in this zone. 1 minus negative 2, positive or negative? Mixed bag. Minus negative means plus. So 1 minus negative 2 is positive or negative? Positive. How come only 3 of you are answering me? Got a room full of people. I got 3 people answering me. Hey, you guys are messing up my YouTube algorithm. Pay attention. They're still not looking. Trying to do this up here. Anyway, 1 plus negative 2, positive or negative? Lots of voices, please. Negative. Good. Okay, so if I have a positive divided by a negative, my overall result is a negative. Then you grab a number between negative 1 and positive 1. I love 0. 1 minus 0 is positive or negative? Positive. 1 plus 0, positive or negative? Positive. Clearly, 2 positives divide to give you a positive. Mr. M, can't we just assume that it oscillates between positive and negative? No, you cannot assume. You actually have to test the zone, especially for rational functions. So let's grab a positive 2. 1 minus 2 is negative. And 1 plus 2 is clearly positive. So yes, this one actually did oscillate, but we still needed to check. Zones where a value is greater than 0 are positive zones. So that's the zone. My domain then is from negative 1 to positive 1. And I cannot include either of those numbers. Negative 1 makes me divide by 0, undefined. Positive 1 makes me try to take the log base 3 of 0, also undefined. So they cannot be included. Yes, ma'am. So the reason why is because anything to the right of this would have continued to be negative, which isn't allowed in my argument, and same thing to the left of that. But yeah, if it had been these zones out here, then I would have had to have used infinities. Alrighty. This last one's really fun, actually. Well, I mean, I think it's fun because I'm a nerd. But it's the log of an absolute value, which is kind of an interesting setup. So you go, okay, fine. I need the absolute value of x minus 2 to remain positive. Now, if the polynomial expression inside the absolute value bars was uglier, like, oh, if it was a quadratic or something inside a logarithm, then you'd have to talk about a sign diagram. But this is literally just saying absolute value of x minus 2. What do we know about absolute values? They're always positive, except for when they're... No. Every value that comes out of the absolute values will be positive, except for... No. What's a number that can come out but is not positive? 0. So every value that comes out of here will be positive, satisfying this condition, except for the absolute value of 0. Because 0 is not greater than 0. What's that? You say that's so dumb? Oh, that's what it sounded like. It's like, how is that dumb? 0 is not positive. Basically, we just have to make sure that x minus 2 isn't 0. So x cannot be the number 2. Because if you try to use x equals 2, man, go home too, you're drunk. If you try to use x equals 2, you're asking yourself, what is log base 1/2 of 0, which is undefined? Your domain then is everything except for the number 2. Everything but 2 works. It is a really neat graph. It's unfortunate that this can't see the graph that I'm about to show you guys. But if you go to Desmos, it does that. It's defined everywhere except for at x equals 2, where there's a vertical asymptote. But I think that's cool because I'm a nerd. Alrighty. Flip them. So do you guys think that you can set your arguments greater than 0 and solve for x and be okay? If you can, then you can definitely find the domain of a logarithm. So question number 2 is a matching question. When you go to do your homework, you are going to see that I have assigned numbers 1 through 8. They're matching questions. So there's almost no work to do. You just match the graph to the equation. So right here, f of x. This is the parent log base 2 graph. This is a parent logarithm graph. A, B, C, or D. Which one is a parent log graph? Just look at them. Which one's the parent graph? C is the parent graph. So this is f of x. We recognize it as the parent graph because it's going up and to the right. It's asymptotic to the y-axis. It goes through 1, 0. It is a parent logarithm. Do you guys remember when we were graphing square root graphs and we were talking about knowing which way it points, up or down, then left or right, judging by the symbols that were on the front or the symbol in front of x? The parent logarithm graphs can be thought of being the exact same way under extremely special circumstances. As long as the logarithmic base is greater than 1, then you can use the exact same knowledge about which way the graph should point. So, here, if you make an x negative, what transformation is this? It's a horizontal reflection. So if you it's horizontal because it's on the inside, and negatives are reflections. So if you horizontally reflect, are you reflecting over the x or reflecting over the y? Okay, so this is reflect over y-axis. So which of these graphs has us reflecting over the y-axis from our parent function? A. Oh, no, B is over the x-axis. So this one is over the y-axis, which is the horizontal reflection. So this one is our g of x. There it is. So putting a negative on the x, like I said, because the base is positive, I can also say, look, because the number on front is positive, it points up. And because the number in front of x is negative, it points left, up and to the left. I can only pull that trick off when the log base is bigger than 1. And that is a trick. It's a trick of transformations. But as long as the log base is bigger than 1, you can ask yourself, does it point up or down? Does it point left or right, just by looking at the symbols? Okay. Here, I've got a negative on the front. What kind of transformation is a negative on the front? Reflect over x-axis. Remember, this is a vertical change, and if you are changing from positive to negatives vertically, you're going over the x-axis. So this is reflect over x-axis. Okay. Which one of these, A, B, C, or D, is the parent function reflected over x-axis? You guys can all shout out correct answers. B. This is h of x. Uh-oh, my phone is ringing. The phone is ringing. Anyway, through process of elimination, we can see that there's only one function left and one graph left. I need you to see, though, that the logarithmic base, excuse me, I was about to say exponential, the logarithmic base is between 0 and 1. So I can no longer say points up and to the left. We could see that this one points down and to the left. How strange that, I mean, we see the y, it's over the y-axis, but it would appear as though making the base a fraction instead of a whole number, and by specifically when I say a fraction, I mean to the negative exponent, acts as a reflection. Very interesting. Very interesting. So we know that this one's k of x. I'm sorry? Why do they skip I and j? Because I means imaginary and j is often, and I-j pairs are often used in vectors. So it's just something that mathematicians do because those two letters are often used elsewhere, vectors and matrices. They try not to name functions them, but that's why. Look, the more you know, right? Okay. Anyway, this graph has clearly been reflected over both axes. It's upside down and backwards. Okay, well then, based on that knowledge, which one of these would have been the graph if we had just only changed the base, but we left the x positive? I would just mean A, B, C, or D. What would be the graph? All right, people weren't quite listening, and it's an important concept. You're all going to want to be listening to this. Again, clearly, this made us reflect over both axes. We know that this means reflect over the y, excuse me. That means that this must have made us reflect over the y-axis, strangely enough. So which graph is this, A, B, C, or D? B, because this made us reflect over the x-axis. So it must be graph B. So we're going to make a statement down here. Not only do we know which is the correct graph, this has also left us with a statement that we can make about logarithmic bases. Giving the base a negative exponent, by the way, that is 2 to the negative 1. So it's the same base, just with a negative exponent. Giving the base a negative exponent is the same as reflecting over the x-axis. That tells us that we could have, instead of saying log base 1/2 of x, we could have written it as simply 1 negative log base 2 of x. These are the same graph. And as it turns out, every change you make to the base of a logarithm is a transformation, not just that one. And we'll get into more of those once we've learned our properties of logarithms. And they're not like they're alien or new transformations, but because of properties of logarithms, they're going to be ways of representing stretches and shrinks and things like that in ways that you'd never really thought of before. Very soon. Very soon. Is everybody cool with this? Think of it because, remember that trick I taught you? Actually, let me get some scrap paper and remind you of the trick that I showed you. There's no scrap paper in there. I'm out. Here we go. Here's some paper. On yesterday's extra credit, I had you guys working on evaluating logarithms, and I told you I was cool with you using the trick. So if I said log base 2 of 8, you would, oh, you can't see that. You would have, and I know that this one's obvious, but you would have done it like this. Log base 2 to the first of 2 to the third, and you would have done this power over this power, and you would have gotten 3. So if we had done this, 1/2 of 8, then that 1/2 would have been 2 to the negative 1. So it would have been 3 over negative 1, which is negative 3. But negative 3 is what you would have gotten if you had just multiplied this by negative 1. And if you multiply the right side of the equation by negative 1, you multiply the left side of the equation by negative 1. So this thing also equals negative log base 2 of 8. So hopefully it's clear why that's working. That making the exponent, making the base of the logarithm have a negative exponent is the same as if you had just multiplied by negative 1 on the front. Okay, doke, smoke. Cool. Ba-doop. We've done this before. We've graphed logarithms. This one is the parent log base 2 graph. We're going to get its values, and we're going to put them on this graph. All right? All right. I'll do it in red and blue. What is log base 2 of 1? Lots of people, please. Log base 2 of 1? 0. Thank you, 2 people. Does that mean the rest of you don't know? It just means the rest of you are ignoring me. Log base 2 of 1 is 0 because that is a special logarithm. Lots of voices would be great. What is log base 2 of 2? 1. What is log base 2 of 4? And what is log base 2 of 8? Great. 1 comma 0, 2 comma 1. Wait. Yeah, I said that right. 4 comma 2 and 8 comma 3 gives me this parent logarithmic. Asymptotic to the y-axis, goes through 1, 0, just like you'd expect, ready to rock and roll. So if we put a negative sign on the front of it, what is that again?
It's like the 1/2 base.
Well, yeah, but I mean, like, but what kind of transformation is that when you put a negative on the front of a graph? Reflect over x. This is very redundant, but trying to really drive it home. So if you reflect over the x-axis, are you changing the x's or the y's? Which one? The y's. And what are you doing to them? You're multiplying by negative 1. You're multiplying by negative 1. So the x's are unaffected, but you multiply the y values by negative 1, which is the rule. You say that every xy is going to map onto unaffected x's, but multiplying the y's by negative 1. That's the rule for that. So if we just plot these points, there's 1, 0, and then 2, negative 1, 4, negative 2, 8, negative 3, looks like this. And we've already said that this would also have been the same thing as if we had just written this. Which we already knew. There it is. But there it is again. For the last part of this question, what we've been asked to do is analyze the two graphs, domain, range, increasing, decreasing, concavity, and Intercepts and asymptotes. Cool beans? Okay. Alrighty, the red one, which is f of x. Domain, is pretty clear, from 0 to infinity. The domain of every standard logarithm, meaning you've just done normal transformations, shifting, reflecting, things like that, is all real numbers. That is the range. I can't remember if I just said range or not. The range of all regular logarithms is all real numbers. Domain range, the red graph increases everywhere. Look, it's an increasing function. And since it's an increasing function, that means it's never going to be decreasing. No decreasing zones. Our concavity for the red one, what do you know about it? Concave down on its entire domain. It's concave down forever. Its intercept is 1, 0. And the asymptote is x equals 0, the y-axis. Since the blue graph, g of x, is the same graph, just upside down, very little of the information changes. It is the same domain. It is the same range. But the blue graph is not an increasing function. The blue graph is a decreasing function. So it never increases, but it decreases on its entire domain. What do we know about the concavity of that blue graph? It's concave up on its entire domain. Its intercept has not changed. And lastly, the asymptote has not changed. Did you just say this class is very boring? Oh. I don't know. When do we get out? At 27 after today? All right, so I got 10 more minutes. Awesome. Yep, 10 more minutes. I'm not finishing the notes anyway. All right, so the last bit that I did with period 2 was these 2 questions, and I called it a day there, so I'll do the same with you. It says, determine the asymptotes, the end behaviors, and we'll use limit notation. The way that I tackle these things is I try to decide which 2 directions it points. First, I notice every one of these is the common log, and the common log has a base that is larger than 1 because it's base 10. And since its base is larger than 1, I can use the same old tricks to tell me which 2 directions it points like you do for square root graphs. I can see the number in front is positive, so it points up. And I can see that the x is positive, so it points right. So just like every parent logarithm that has a base that is larger than 1, it looks like that. So this graph, which 2 directions does it point? Up, because it's positive on the front. And points to the right because the number in front of x is positive as well. So this one points up and to the right, like this. And what we know is our argument must remain positive. So if we add 1 to both sides, we get that x better be greater than 1. That tells me that this asymptote is at x equals 1. And now I'm ready for end behavior. The limit as x approaches positive infinity of my graph. As I go to the far right, my graph it's slow, but it will continue to go up forever. But as I go to the left, I am going to slam into that asymptote. So I say the limit as x approaches 1 from the right, which means I need a tiny little plus sign. And at the asymptote, it shoots down. There it is. Last one for today. Again, base larger than 1. It's a base 10 logarithm, which means I can see which two directions it points just by looking at it. Because the number in front of the log is a 1, is positive, which direction does it point? Hold on. Okay, so 2 people answered me in a classroom full of people. That's crazy. Because the number in front is positive, which direction do I know it points? Up. Because the number in front of x is negative, which direction does it point? Left. So this graph points up and to the left. Like so. There it is. We just need to find the asymptote now. We could see the end behavior as long as we know where that asymptote is. And remember, the argument must remain positive. So 2 minus x must be greater than 0. If you add x to both sides, you get this statement. But it's written backwards, but you see how the little arrow points to the x? There. That tells me that my asymptote is hiding out at the number 2. So this is at x equals 2. Ready for the limit notation. The limit as x approaches negative infinity, so going to the far left. Well, if I go to the far left, it's going slowly, but the graph is going up. But as I go to the right, I am going to slam into an asymptote. So the limit as x approaches 2 from the left side. And that is when it goes down. And I guess we'll call it there today. That feels like a good stopping point. Deuces.